My guest today is Robert Cutler.
It's a great pleasure to be here and to share with you and your followers a really exciting discovery, and that is that climate repeats after 3,560 years. I don't think that was expected, and is probably not expected in a lot of climate circles either. But anyway, the implications of this are fairly significant, I think. It's going to allow us to understand natural variation quite a bit better. And because climate repeats, there's got to be a periodic forcing function in there somewhere. So we'll see how this plays out over time. But this is exciting and, like I said, entirely unexpected. Now, my background is actually engineering. I've specialized in kind of signal and systems analysis, and I've worked on everything from mechanical systems, rotating machinery, vibrations, control systems, up through RF communications, all the way up to millimeter waves. So quite a few different wavelengths, Tom. But anyway, I wasn't involved in climate until about 3 years ago when I was kind of minding my own business and read an article one day. I won't go into all the details, but the upshot was I found that I could predict, or appeared to be able to predict, temperature from a moving average of sunspot data. Now, that took about 1 cup of coffee to discover, but it took me about another year, a little less than a year, to figure out why it worked and that it wasn't a spurious correlation. And ultimately, it boiled down to I could explain it, but only using the Jovian planets, which is why we're here today, actually. So if I'd picked 50 years, we wouldn't be here. But I accidentally picked a 100-year moving average and got something that looked just like this. Now, the problem was, how do I convince anybody? And my goal was to find something so convincing that even a skeptic wouldn't be able to deny it. But that turned out to be an extremely challenging problem because even if we can predict solar activity, we don't have good models for how that affects climate, especially climate at some location. You know, how do you go from solar activity to climate in Greenland or New York or something like that? We don't know how climate affects Earth or how the sun affects the Earth, for example. It may have feedback mechanisms that we're not aware of, including cloud generation or creation and that sort of thing. So that turned out to be a problem. I couldn't have any physical models. And that left empirical models, and that was a dead end as well, because the more I got into this, the more cycles there were. There were too many cycles. And then when you start adding the fact that the sun and probably Earth are nonlinear systems, we end up with lots of harmonics of those cycles and beats between the harmonics. Just so many problems that if I did build a model that was empirical, it would have so many tunable parameters that I would rightly be accused of overfitting. So that wasn't going to work. But everything I looked at was really encouraging in terms of, yeah, it's got to be the sun, and somehow the Jovian planets are involved. So this is a plot, this red trace is a plot of Greenland ice core temperatures, the spectrum computation. This is the alley reconstruction. And the blue trace is the spectrum of the sun's motion around the Barycenter. In this particular case, it's acceleration, but the velocity spectrum looks almost identical. And you can see we've got kind of something going on at 900 years, and there's something going on around Neptune, and something going around Uranus, and then this 61-year cluster. And so it's really encouraging, but the devil's in the details. And this is an 892-year cycle, and for the acceleration, this is 937, and for velocity, it's 925. Close, but not quite. And this could be a frequency estimation error, but as we'll see later in the presentation, I can also explain an 892 or an 890-year cycle anyway. Same thing here. 165 is Neptune's orbit. This could be a frequency estimation error. How accurate is the reconstructed temperature data? But I can also explain this cycle in terms of the Jose cycle and one Jupiter-Saturn conjunction, which gives me this. And my research has led me to believe that that's actually a legitimate number. So at the end of the day, it was looking kind of hopeless that I'd ever come up with something that would convince a skeptic. And Tom, that's when a miracle occurred. So I found this one combination of cycles in one way and a product of 4 times another cycle I'd discovered another way. And 3560 was not a number that I'd seen pop up before. So I was kind of curious. So I went and got one of my favorite reconstructions and do what I often do, which is just shift it over to see if anything at all aligns. And I just about fell out of my chair when I saw this. It's almost a perfect alignment. Now, there's a couple of places where it doesn't, like here and here's, they seem to be temporally aligned, but inverted in phase. And we'll explain what that might be here. And there's another one over here. So this is really amazing. How can you expect a really complicated waveform like this to repeat? And it turns out that, while 3560 technically is a cycle, it's also a framework within lots of other cycles exist. So if we divide this by 2, we could get 2 1780-year cycles. There's 3 1186-year cycles, and so forth and so on, 60-year cycles. So we can have a very large number of cycles in here. And the beauty of this technique of doing the shift analysis, and the beauty of having a bunch of harmonically related cycles, is we don't have to know what they are. So, you know, I could have all of these. I could have 5 of them, and I don't have to know what their magnitude is, and I don't have to know what their phase is, because as long as there's an integer number of cycles in 3560 years, when I shift it, they'll look the same. And so that's what's going on. And that's really important, because as we'll talk about in a second, all climate is local. So a local climate might emphasize some of these cycles if they're there and de-emphasize others, for example. Now, these inversions were confusing, but I think I figured out what's going on. So there's a well-known 2400-year cycle. Sometimes it's given as 2200, sometimes longer than 2500, but it's called the Bray cycle or the Bray-Hallstatt cycle. And let's just say it's 2400 years. Well, that's close to this value. Well, if I had a Bray cycle in this temperature data, and I shifted it 3,560 years, because there's 3 of them here and double that amount, I'd only have 1.5 of them in here. So it's quite possible that a 1.5 cycle shift might appear inverted. And the same thing with bond cycles. We might have 2.5 bond cycles in here, for example. So that's what's going on. So what I hope to do today, Tom, is convince a lot of you that climate repeats after 3560 years. And this doesn't involve models, just to involve looking at data and seeing that it repeats. So that's my goal, is to convince you that we do have a 3560-year repetition in climate. And we're going to look at it at multiple locations, because we should expect to see something at multiple locations if something like the sun is a common forcing function, or the planets themselves are a common forcing function. And then we can argue about where the 3560 comes from, and that would be healthy, I think. So what I'm going to do, though, is show you how I came up with that. And so we're going to link the cycles of both the sun and Jovian planets to this number, a few other things. And what it said, other cycles. And then finally, we're going to link some of the cycles we have to rapid warming and cooling events. Now, this is a bit tenuous. I can't explain what we're going to see here, but there's a lot of coincidences. And that may offer a better explanation than there were a lot of volcanoes, or we got struck by an asteroid or something like that. Okay, well, we're going to have to use proxies. I'm sure most of you listening to this know what proxies are, but in case you don't, there was nobody sitting around recording temperature and carving it into stone tablets 5,000 years ago. So we're going to have to kind of go somewhere, drill in a core like an ice core, and these will have layers in there. So we'll have to date that layer and then extract material from that dated layer, and from isotope ratios and stuff like that, we can make determinations about various things, such as what temperature might have been. Now, this technique that I'm showing you places a lot of constraints on ice cores. They are on proxy data. They have to be very high quality for 2 reasons. First of all, if we're going to shift something 35, 60 years, then we're going to have probably 7,000 years worth of data in order to get significant overlap. So that's the first constraint. It has to be fairly long. The second constraint is, because the 35, 60-year cycle is actually a framework containing lots of faster cycles, probably even faster than 60 years, probably 20 years, probably faster than that. We need very high resolution in that proxy data. Now, the best data we have, and that's what I'm going to show you first because it looks really good, is the Greenland ice cores. And these work really well. They have the length, but they also have often annual layers because it snows there quite a lot. So researchers that do this work, and they're amazing, a group of people, they do amazing work. But often they can resolve layers annually because they can see the individual snow layers, and that helps with dating as well. Now, Antarctica is a different story. So the Antarctic ice cores, they offer longer records, often much longer, but we don't need much longer, for what we're doing here. But they have significantly less temporal resolution, and they also appear to be noisier, simply because it doesn't snow as much. So we're going to try and extract some information, but I'll warn you up front that it's going to be a little harder to see, and we're going to have to use correlation techniques to look at that. And then finally, there aren't any ice cores at the equator, so we're going to have to use sediment cores. We've got a couple that I found. These are kind of hit and miss. A lot of them don't have the length, or if they have the length, there may be huge gaps in the data. Or if they don't have gaps, a lot of times they'll have sample rates that are high for a while and then low for a while and everything else. But I have found two interesting sediment cores, one from a lake in China and one from a lake in Alaska, and we'll take a look at those. Now, we're going to use, these are our three best data sets here. This 3 ice cores, they're separated by several hundred kilometers or several hundred miles, however you want to think about it. The Neem ice core, the Ingrip ice core, and the just 2. And there's a tendency in a lot of climate research to combine these things and say that the average of all of these things, or some other way of combining them, means that's what Greenland climate is. But if you think about your own location, if you move 400 kilometers away, the climate's not going to be the same. There's probably going to be a mountain range that causes things to be different, stuff like that. So with what we're doing, and because we're relying on very high resolution data, we can't combine things. We have to look at them individually, and that'll be obvious in a second. Now, one of the reasons for that is I tried to draw an analogy here. It's the same problem that we have in acoustics. If you've ever gone to a concert hall, you may have noticed that some seats sound better than other seats. And if you have a place you listen to the radio or a home theater system, you might find that while it's the same song everywhere in the room, if you move around in that room, it sounds different. And that's because the energy takes different paths, and how they combine at your location can vary quite a bit. So in acoustics, we might emphasize some frequencies and de-emphasize others. So for example, it might sound great here, but if I move off to a corner, it might sound kind of boomy because some of the low frequencies are constructively interfering and causing a more strong low signals, for example. So with climate, think of the common forcing as being the sun, and think of all this multipath, which is what that's called, as being the various heat transport mechanisms in geography and things like that. So we don't want to combine things. And just looking at the data here, so this is 3 different sites, and without looking at it very closely, you can tell they look different. They're all different. This one has much better timing resolution, and there are features that kind of match, but there are a lot of features that don't match as well. So let's start up here in the upper left corner. So this is the GIFS2 site. And by the way, all of these are Martin and et al. Reconstructions. They were all from the same paper. So that reduces one variable at least in what we're doing. But this blue trace is the reconstruction of temperature for the GIFS2 ice core site. And the red is that same data shifted to the right 3,560 years. And you'll notice there's a dashed line there. I put that there to draw your attention to this event here. So this rapid cooling and rapid warming, this cold event is called the Younger Dryas. And the 3560-year shift causes that rapid warming event to line up with this negative temperature spike, which happened 8,200 years ago, and hence it has the name the 8.2 Ka event. So we're going to look at that in more detail later. But this 8.2 Ka event, when it shifted over, lands right here. And that point on this expanded trace is this point here, which I cut off so we can see things a little better. but a very large negative spike. Well, that lines up with this other cooling event, which is known as the 4.7 Ka event because it happened 4,700 years ago. And if we shift that over, that lands about here, and that's the Dark Ages cold period. So at least in cold periods, we seem to have this 35, 60-year period. Now let's take a look at the in-group data because this is the easiest one to see, and I'll explain these green bars in just a second. But if we look at this in-group data, it doesn't take much imagination to see that these match with a fairly complicated pattern from this edge all the way up to that black line. And then they kind of go different, and then they come back together again and match up again. And we can see the same thing down on the Neem site. If this one needs to be kind of detrended, but if we bend this up, you can imagine those matching. But these two match here, and again, we can follow this along, and it matches itself pretty well. In fact, you might even argue it matches itself better than it matches the other sites. Okay. Now, these green areas, these are where we saw the inversions in the animation. The animation was a data set by Ali. And so I set the width of these more or less based on that lower resolution data because that reconstruction is heavily filtered. And that gave me a little bit of room to spot things moving around. So what we're expecting to see with these green is that things somewhere in there don't match. And we see that in here, they don't match, and here they don't match. And here we have a mismatch here, and up here we have something going on. Now, these black lines are not placed based on any temperature reconstruction. These black lines represent the point in time when all four Jovian planets, Jupiter, Saturn, Uranus, and Neptune, are all in a line. And that happened in 1306, and it happened before that in minus 3321 AD or 3322 BC. And there seems to be some correlation on these two regions with where these inversions might be occurring within proximity to that. Okay, so that's kind of interesting. Now let's take a look at this just two data because this is just really amazing to me. This is high resolution data. So some of these fast edges that you're looking here, they transition 1 degree in less than 40 years typically. That's the kind of resolution we have in here. And yet, if we look through here, we can see even with 40-year resolution, a lot of things match. And then we see things that may be mismatched, but that might be real. I don't know with this kind of resolution. But this follows along, and there's many of these events that structurally match extremely well. This point might be misplaced, or that point might be misplaced a little bit. This one has kind of a fine grain ripple. This one has the newer ice has a coarser grain ripple. But this is absolutely amazing. And let's just think about this for a second. What are the chances of being able to do this? I mean, that we're dealing with ice core data, and we're dealing with people interpreting that ice core data and trying to figure out what the timing is over thousands of years. So that's one confounding factor. And then the Earth has probably changed in 3,000 or 4,000 years. Oceans are going to have a different amount of heat content. Some places might be desert. Some places might have forest where there used to be desert. The ice caps will be different. Glaciers might be different. And yet, with all of those confounding factors, we can take this and shift it over 3,560 years and have all this stuff repeat. To me, that suggests that whatever the forcing mechanism is, it's not subtle, it's strong. And so when we look here, especially at the in-group, you say, well, how much noise is in there? Well, it's not very much. So this tells me right away that a random weather, which we know is chaotic, climate is not the summation of random weather. This is driven. So the top trace here is the alley reconstruction. So that's the one I animated. And you can see here where I've defined these green areas to kind of where the alley seemed to be inverted or possibly. Now, I mentioned a 71 20-year shift. So if I shifted 71 20 years, we see this. Now, just to get our landmarks here, this is the Holocene area, the interglacial that we currently live in. You are here. And so this is a nice warm period. We're all really happy here. Before that, 12,000 years ago, it was a lot colder, and there were these random looking warming and cooling events called Dansgaard-Oskar event. I'm going to butcher all of these names. Sorry about that, Tom. But, we're going to have these rapid warming and cooling events. And what's interesting, after 7120 year shift, we have one of these that seems to align, and a few other points that may be doing something interesting. But if I shift it 4,627 down here at the bottom, we see some other things align. So we've got two periods now that at least in the glacial period, it may be a little bit more complicated. And the bond events are typically given, are defining these as being kind of 1470, but here we see it might be a little bit more complicated than that. But what I really want to draw your eye to is this point over here, the bottom, very bottom right. So remember when we did a 3560 year shift, the termination of the Younger Dryas lined up with the 8.2 Ka event. And after a 4627 year shift, the onset of the Younger Dryas lines up with the 8.2 Ka event. I find that fascinating. And we're going to look at that in more detail later. Now, getting away from the poles, now we're relying on data that's a little harder. The proxy data and sediment cores and stuff, I think, must be a little bit harder to date and harder to interpret. But this here is data from Tianka Lake. It's at 29 degrees north latitude, so we're well away from the poles now. This is a lake up on the edge of the Tibetan Plateau, if I'm not mistaken. So it's a little harder to see, but we can definitely look in here and we can see some general trends in here where it seems to match pretty well. Far over to the right, there's something that looks a little bit more obvious. This is a little more of an ice stream, but what's interesting is when we get to this green area where we expect something to be inverted, it's definitely inverted there. There's definitely some things going on here, which it's hard to say, but it's inverted where we expect it to be inverted. Same thing kind of here, although it's a little dicier perhaps. So anyway, we're going to use correlation analysis on this one just to confirm what we think we're seeing. And then in Antarctica, we have the Epica Don't See data, and this is much noisier. So I'm not going to try and point to something and say, see, it matches and expect you to believe me, because you shouldn't. So we're going to use correlation analysis to see if there's anything lurking inside of this data. Now, I said that solar was involved. So I've got a couple of reconstructions. The top one is by Steinhilber. This is a reconstruction of total solar irradiance, or basically how bright is the sun. And if we shift at 3560 years, we at least see some things in here where there are spikes that seem to kind of align. A little noisier to look at. The sunspot number by Wu is very similar. Now we have to be a bit careful with this because these reconstructions are also using Greenland ice core data and data from Antarctica. They throw in some tree ring data and maybe some data from caves or something. I don't remember, but we always run the risk that we may be fooling ourselves with these because they're using data from the same sites. But that's interesting. So one of the things that we'll notice in here is that we've got this big red droop that didn't line up with a droop in the blue trace, but then in the blue trace, there's a big red droop that doesn't line up with one in the red trace. But if we shift things 3,560 years, those line up, as well as some other touch points. And these points, by the way, are the various minimums we talk about, the Maunder minimum and stuff like that. So it appears that these global or these grand solar minimums that we see during the Little Ice Age also occurred 7,120 years ago, possibly, looking at this data. So the top trace is yet another just to reconstruction. This is a little older by Groots, and the only reason for bringing this up is this particular reconstruction goes back a little further in time, and I just wanted to highlight that there might be kind of a 71, 20-year pattern going on in here. Here's the one we saw before in one of the other reconstructions. So there's definitely something that could be going on there. Now, this middle panel, this is fascinating. So this comes from a sediment core from a lake in North Alaska. It's called Lake E5. And let's just focus on the blue trace, forget the red trace for the moment. Well, actually, before I do that, let me talk about this region here. This is one of those sediment cores that I was saying has variable sample rates. And I actually put the sample rate down here so you can see what it's doing. But in this region here, we got fast sample rates, and then we got low sample rates, and then who knows what's going on here, but it's very, very ragged. So when I first looked at this one, I kind of put it in where a lot of the other sediment cores were, and it's just too noisy. And it was to do anything useful in the Holocene period, the interglacial. But down in the interglacial, something caught my eye because there was some structure in here, and I hadn't seen any structure in the Greenland ice core data in this period of time from minus 30,000 AD to minus 10,000 AD. But what we see down here is these periodic spikes, and they line up very well. I kind of looked at that and said, okay, what is that? And you can kind of count them and then divide by the number of spikes. And it came out to be 1850 years. And that number caught my attention because I already knew about a 925-year cycle in the sun's motion. I mentioned that earlier. So I put dotted lines here, and they're evenly spaced at 1850 years, and they line up extremely well. Obviously, these are a little coarser. They line up extremely well with these rapid warming and cooling events during the glacial period. But more interestingly, they also kind of bookend this period here, which is known as the Balling-Ellerod interstadial, or the BA interstadial. So that was really interesting. And as we'll see in the next slide, where we do some correlation analysis, this periodicity, this 1850-year periodicity, appears to continue on through the Holocene. And we'll see that in the Greenland ice core data, and we'll see it misplaced a little bit, but I'll explain that in the Lake E5 data from China. So this is a busy slide. Let me explain a little bit what we're looking at. First of all, we've got all these panels of the different reconstructions. So we have the GIST-2 by Ali, the GIST-2 Ngrip and Neem by Martin et al. We have our Tiankou Lake data here. We have the Antarctica data, the Epicodome C data. And then one of the solar reconstructions, in this case, sunspots. Okay, so that's what we have here. This is, ignore the red, that was just a shift, but the blue trace is the detrended data for all of these reconstructions. And what I did was I took a 2,800-year chunk of this data and compared it just by placing it down and then sliding it over. And every time I slid it over a little bit, I compared it. That's called correlation analysis. And I chose 2,800 to avoid any numbers that I had seen. And I tested the sensitivity on that to make sure that it wasn't sensitive to it. And it wasn't. But anyway, I took a 2,800-year chunk and then slid that along. And what you'll see in every one of these reconstructions is a correlation peak at 3560. It's quite visible, slightly misplaced in the GIST-2, surprisingly. The Martin, which has very high resolution, you can see that's a nice sharp peak. The Ngrip data, the Neem data, the Tiankou Lake data, it's a little skewed, but it has something there. The Epicodome C, which was a real ice strain, and you can see why, because there's nothing really popping out in all of these data. But even in spite of all of that, there was something near 3560. And all of these also have some peaks that may be 4627 plus or minus 178 years, but I'm not going to talk about those. Now, we also had a 27 or 2670 year peak. I don't know where that's coming from necessarily, but we'll find it's harmonically related to stuff we're interested in. There's our 1850 year peak. And when I saw that again, and I thought, well, this has got to be 925. But if I put 925, it doesn't work very well. So 937, it might be. It's hard to say. It could be either one of those or neither one of them, but something here. But anyway, the 1850 year cycle shows up in all of these, all the way except down to Tanka Lake, and not in the Epicodome Sea and not in the sunspot data. But this Tiancao Lake is worth a little bit of discussion because I think there's a dating error somewhere in that data set. And the reason I say that is if I take a different 2,800-year chunk and do the correlation analysis with that, this point lines up at 1850 and then the 3560 shifts. So there could be just something as simple as a dating error in there. So I'm going to claim that that's probably 1850 in there. So that gets us to kind of the end, Tom, of is there a 3560-year cycle or not? And again, we don't have any models here. This is just taking data as we find it and comparing it to itself. So before I get onto kind of where the origins of the cycles are, do you have any questions or comments?
Probably too soon to ask, but according to what you've seen, what does this mean for the next 100 years, for example?
Oh, you're going to pin me down on that, are you? Well, I think it's a little dangerous to make predictions because there's, as we saw from the inversions, we don't fully understand where those may occur. And so I don't know, but if you want to play around with it and have some fun, when we look at the ALI data, that was kind of interesting because it has us in the middle of a sudden warming period, and that peak, if you go back 35, 60 years, is the Minoan warm period. So we may be reliving the Minoan warm period, but there's also other cycles in there. So a 35, 60-year shift doesn't necessarily tell us everything. But everything I did look at, all of them had, whether I did a 71, 20-year shift or a 35, 60-year shift, all had a peak around 2200, they're plus or minus, so peak temperature. But some of them alarmingly had us getting cold, possibly. But then again, I'm predicting climate in Greenland. So who knows what's going to happen here. So anyway, yeah, we'll maybe come back for questions later. Thanks for that one. All right, well, let's talk about now we're getting into stuff that is slightly more speculative, but I don't think we can argue about the 3560, especially looking at the Greenland data. If you can't see that, you're just a cycle denier. What can I say? So anyway, let's talk about where this might come from. And, I've spent a lot of time the last 2 years. So it took me about a year to figure out what was going on. And then I spent another 2 years studying the motion of the sun around the Barycenter and the structure of the spectrum and lots of other things. And it's definitely got all the hallmarks of a resonant system, plus a few other things I'm not going to talk about. So I thought, well, I can explain this as a spring mass system. And this obviously isn't technically correct. These planets are orbiting, they're not connected by springs, but this will serve for our purpose. But really, we have two fundamental questions that we have to answer. And the first one is, can the Jovian planets modulate solar activity? These haven't been looked at a lot because the belief was they were too far away, they couldn't affect the sun, and so no, they can't. But we're gonna revisit that. And then the second question might be kind of surprising to you, Tom, but is, do they need to modulate the sun? And I'll talk about that more in just a second. Let's tackle the first question. So can the Jovian planets modulate the solar activity? Well, admittedly, Uranus and Neptune and possibly Saturn are too far away from the sun to have a direct impact on what's going on. Jupiter is pretty close, and if you're into tidal forcing models, Jupiter and Venus or Earth are often used to try and predict sunspot cycles and stuff like that. I'm not going to go into specific mechanisms here. It's just a question of how can we possibly see something that's so far away? Well, here you'll see that I have a spring between Neptune and Uranus, but I don't have a spring connecting Neptune to the sun. There is no direct connection. It's too weak. But when we start thinking about this as a system, then we can start to see how the influence of these planets on this planet, for example, which then ultimately affect Jupiter and ultimately affect the inner planets if we need to. So let's just take Uranus and Neptune, for example. So they have a conjunction every 171.4 years. And during that conjunction, they basically swap angular momentum back and forth. And that may or may not be a perfect swap. And if it's not a perfect swap, then the orbits of these planets are shifted slightly. And that means next time we come around, it might behave a little differently. And same thing between Uranus and Saturn. They get together every 45 years for their swap meet. And again, that may not be a perfect swap of angular momentum, so the orbits can be changed. And then Saturn, of course, interacts with Jupiter every 19.86 years. So we can see how these things can cascade in and back out again. And so there is a mechanism by which the outer planets can be felt on the inner planets, or Jupiter, for example, which is close enough to potentially modulate solar activity. But I will say, if it is, it has to have some amplification mechanism, because these are pretty weak. But that's okay, because the sun is a very nonlinear place, so maybe it doesn't take much of a nudge to cause the fusion to flare up a little more, just to kind of put a graphical picture to it. But let's ask the question, do they need to? Now, this might sound like an odd question, since I'm saying 3560 comes from these orbits. But let's think about the sun for a minute. It's 99.87% of the solar system mass. And in my book, that's a lot. And Jupiter is really only a 0.1%, not even that. So you could almost envision Jupiter as a bobblehead doll attached to your dash. You know? It's going to bounce around, but it's not influencing the car very much. So what can possibly explain why we don't need these? Well, inside the sun is the nuclear core, and that's a solid fusion core, and it's about 49% of the mass of the sun. Okay, so that means it's about 49% of the mass of the solar system. Now, anybody that's ever worked on mechanical or electrical systems know that anytime you have something that possibly has resonant modes and you have a source of energy, it's probably going to oscillate. So for electrical engineers, that turns out to be, you tried to build an amplifier, but the amplified signal somehow got fed back and caused it to oscillate. That's like turning the gain up too much in the sound hole too, is where you get microphone feedback. For mechanical engineers, aerospace engineers, the problem is with wings. If you get a wing and it has a resonant mode and the airflow is putting the right energy into the system, that wing can resonate, and that's called flutter. And if you get into a flutter condition, that wing's going to vibrate off, and that can ruin your whole day. Also, I don't think there's very many, I've never met anybody, but I don't think there's any engineer or probably physics major that hasn't seen Galloping Gertie. Have you heard of that one, Tom? Galloping Gertie?
I sure have. Yep.
Yeah. So that was a bridge near Tacoma, Washington, a very famous bridge that right after they opened it, the winds kicked up. It excited a resonant mode. And the bridge deck eventually, after twisting around for a bit, collapsed and fell into the water. So now I have a hard time having worked with a lot of these kinds of systems. I'm not a astrophysicist, obviously, but I have a hard time imagining that nuclear core doesn't have resonant modes. Okay. And it's big, it's heavy, it's massive. So those aren't going to be little 3 hertz resonances. They're going to be long cycles probably, and lots of different versions of it. So let's say that it does have a resonant mode. In fact, let's just assume it has a resonant mode that's 178 years. What would we expect? Well, we might expect the planets to somehow exhibit behaviors consistent with 178-year gravitational waves. Okay. Also kind of correlated to that, highly correlated to that, the core is going to be creating pressure waves. And these pressure waves have the potential, and they're acoustic, so they can travel quite quickly within the sun. Those are going to potentially modulate the density of the radiative zone. And that's going to modulate the amount of energy reaching the convection zone. And the convection zone those convection cycles are probably going to speed up or slow down based on the amount of energy they're getting. And so sunspots, the periodicity of sunspots in particular, would be another indication that solar output is varying. And it's a different mechanism, but what I'm trying to say is that sunspots are a proxy for solar activity, and the orbits of the planets may be a proxy for solar activity. Just trying to get people to think outside the box a little bit on this, because if we have the number 3560 and 7120 and a bunch of other numbers, those are fact. Now all we have to do is figure out what the mechanism is. So it's good to think outside the box on some of these things. Now, like I said, if 178 years was a resonant mode, we might see something in the orbits of the planets. In fact, Scafetta, in several of his recent papers, made a good observation. If this is the spectrum, the blue is the spectrum of the sun's motion around the Barycenter. He uses velocity. I tend to use both velocity and acceleration, but they look the same. These red lines are harmonics of 1 over 178. So the frequency associated with Jose cycle is 1 over the period. And so these lines are spaced at, 1 over that, 2 over that, 3 over that. And look at how they line up with the conjunctions like here's the orbit of Saturn at 29 years. Here's the Jupiter-Saturn conjunction at 19.86. Here's the orbit of Jupiter here, so forth and so on. So we've got this 45 years, that's the Uranus-Saturn conjunction that I talked about earlier. So this is really interesting. So we possibly have an explanation for why these orbits and these beats are structured the way they are. Just a theory. I'm not an astronomer. I'm not an astrophysicist. That's the standard disclaimer there, Tom. All right. Now, regardless of where it comes, I'm going to treat the solar system as impulsive. And what do I mean by impulsive? Impulsive signals have basically fast rise time, fast fall times, and then kind of a quiet period between them. So here we have Jupiter and Saturn. And as Jupiter approaches Saturn, the distance between them decreases, but the gravitational attraction between them increases as 1 over the distance squared. So it's nonlinear. So it rapidly increases until we get to the closest point of approach, which I've shown with a red arrow here. Now, if we get the planets kind of spinning around, and this is not for navigational purpose, by the way, if we get these spinning around at some later point in time, they align back up again. But because the orbits are non-circular, we end up with a different distance. Okay. So we have this impulsive signal and we get another impulse, but it's not the same amplitude. Now, why do I keep going on about impulsive signals? Well, I keep going on about impulsive signals because impulsive signals have a lot of harmonic energy. In fact, they have both even and odd harmonics. So if this is 19.86 years on average between these two impulses, the second harmonic of that would be half the period, so 9.9. And the third harmonic would be a third of the period, or 6.6. So we can get a lot of cycles out of these conjunctions that are harmonically related. Now, I just kind of wanted you to understand where this waveform comes from, because we're going to see a lot of it in the next two slides. So I was able to download from NASA's JPL Horizon system 20,000 years worth of orbital data for the planets. And what I did is I went pairwise. So the top panel here is Jupiter-Saturn conjunctions. The third panel is Saturn-Uranus conjunctions. And the fourth panel is Uranus-Neptune conjunctions. Let's start down here. Now you can see that little impulsive signal in there. And you can see that for this one, it's modulated, but it follows kind of a sinusoidal pattern. And we can see what the phase of that pattern is, if that's important to anything. I kind of fit a sine wave to that, and it has a period of 4,271 years. And we'll see that number later in a table of subharmonics. Okay, now I want to get back up here to Jupiter-Saturn. So these are too close together to resolve the individual impulses, but that's okay because it makes it easier to see this yellow sine wave, and that sine wave has a period of 937 years. And interestingly enough, that value holds for the entire 20,000 years period. So minus 10,000 AD to plus 10,000 AD. Now, what does change, though, and it's easier to see, I guess, against the twice the 937, which is 1874. That's this green trace. It's a little hard to see here, but you can see it here. What does change as the orbits of Jupiter and Saturn vary over time is the variance in this. So out here, we don't have quite as strong a conjunctions, and they don't get quite as weak. Does that have any meaning? I don't know. But over this period of time, we're sliding into an ice age, or a glacial period, I should say. We're sliding into a glacial period. So that's worth looking at. It's just an observation. The other thing that I'll point out on this scale is that the period between Jupiter-Saturn conjunctions is not constant. It's 19.86 years on average, but it actually varies quite a bit. And I went in and looked at it, and it too has a 937-year component to it. All right, let's zoom in a little bit here. And now we can see what this 937-year line was following. And here's our twice 937-year cycle. And so what it was doing is it was kind of seeing these 60-year patterns. So this is a high, low, low, high, low, low in terms of the gravitational force between the planets, which kind of reaches a minimum around right at this point in time, which is around 1550 or so AD. So kind of in the middle of the Little Ice Age. Don't know if that means anything, but that's where it is. And then here we have the average period of the conjunctions, which might be important if you have a model that relies on the torque of the planets. This one has a different minimum. This has a minimum around 1650, which, again, coincidentally is around where the modern minimum is. Again, I don't know that that means anything, but we have that. But one of the things I'll point out here, I don't want to go down this too far, but I mentioned how we can get harmonic energy. So that's half the period, a third of the period, so forth and so on. So if we start with 19.86, we had a 9.9 and a 6.6 and so forth and so on. These non-circular orbits also produce subharmonic energy. So here we have a 19.86, a 19.86, and another 19.86. So this 60-year interval is actually the third subharmonic of 19.86. So 19.86 times 3, which is just a little bit less than 60 years. But we can see that it varies over time. So that's actually going to shift a little bit in phase. Now, what I want to draw your attention to is this point right here. So at this point in time, we have a Jupiter-Saturn conjunction, which is unremarkable by itself, but it's in perfect alignment with a Saturn-Uranus conjunction, and it's in perfect alignment with the Uranus-Neptune conjunction. And if we plot that on a solar system simulator, we get what we might expect, which is all the planets are aligned. And in this data, I found that these occurred every 4,627 years, and I mentioned this before. So there's one that occurred at minus 3321 AD, and there's one before that and one before that. Now, what's the significance of this? Well, don't think of this, at least in terms of forcing on the sun. The fact that Uranus and Neptune are lined up with Saturn and Jupiter really isn't important. These aren't, Jupiter's got enough force all by itself. These aren't really lending any aid to Jupiter in terms of modulating the sun. Now, it might be indicative of that solar internal oscillation, if that exists. That might tell us something about that. But what is significant about this is it's a timing event or a phase reference event. So in a little bit, we're going to look at an 890-year cycle, and that has a peak amplitude. One of the peak amplitudes occurs at minus 3321. Okay, so that's a phase reference event for that cycle. Now, that 1850-year cycle we saw in the Lake E5 data, Tom, that one, and we saw it continued through the Holocene from the correlation data. Well, if you compute where that's going to land, that lands around here as well, minus 3321, which is interesting. I haven't associated anything with this particular alignment. So this one seems to be more important, at least on the cycles that I found so far. Now let's talk about the sun's motion around the Barycenter in the Jose cycle. So the sun orbits this black dot. That's the solar system Barycenter, or the center of mass. That's the point the Earth actually orbits. Sorry to disappoint some of you, but the Earth does not orbit the sun. It orbits this little black dot, which is kind of an imaginary center of mass. And the sun orbits that too, a fairly complex pattern as the planets drag it off in different directions, particularly Jupiter. So anyway, back in 1965, a guy named, I think it was Paul, but Jose anyway, figured out that pattern sort of repeated after 9 Jupiter-Saturn conjunctions. So if we compute the radius from that dot out to this line and we plot that radius over time, it follows this kind of pattern. And if we get to the end of 101 of 9 Jupiter-Saturn conjunctions, and we start over on the next and plot it on top of it, we get patterns that look like this. Now, this is all well and good, but it created a problem for me because I can't fit 178.77 years into 4627. And yet all of the planets were lines, and that seemed important. So I did a little bit of analysis on that, and sure enough, the closest I can get to one interval, so if I start at -3 and 321, the closest I can get to 1306 is 1325.9, which is 1 Jupiter-Saturn conjunction too long. And you can kind of see that in the pattern here. This little double whoop-de-doo here shows up here in the first version. So I said, well, what happens if we just take a 178-year segment from the first Grand Jovian alignment, and we take a 178-year segment from the second Grand Jovian alignment, we lay those on top of each other. That's a perfect match. I mean, or darn near perfect match. So what that tells me is that the average Jose cycle is actually 177.96 years, which is 4627 over 26. Now, here's a little interesting thing, Tom. So I said we were off by 1 cycle after 4627, which means we're going to be off 2 cycles if we go another 4627. But there's 9 Jovian or Jupiter-Saturn conjunctions in here. So that should come back around after 9 4627-year cycles, which is 41,000 years, approximately. And some of you may recognize that number as the same general period of Earth's obliquity, one of the Milankovitch cycles. So just an aside. When you study this stuff, you run into all kinds of coincidences. So let's talk about the 890-year cycle now. I've put behind this, I've drawn, this is me drawing this little light magenta, pink if you must, background is to help you see this cycle in here. This cycle was extremely hard to find. It doesn't pop out at you, but this is in the acceleration data of the sun around the Barycenter. This is something I put behind the data. It's just to help you visualize it. Now, this cycle was really hard to find because it is buried in there. In fact, I had to filter off the Earth, Venus, and kind of data in here to make it easier to see. But it doesn't show up in the spectrum of the sun's motion because it's not a 900-year cycle. It's a beat between faster cycles. And so the only way to analyze this was to go find kind of where the maximum seemed to occur and then look for symmetry around that point. So these are kind of symmetric around that point, and I define that then to be a peak. And I had fully expected this to be one of those 925 or 937, but it wasn't that at all. It was actually a lot more interesting. So I analyzed this, and I did all 20,000 years worth of data, and you can thank me later for that, whoever. But what I found was really amazing. These intervals take on 3 distinct values, either 883 years, 854 years, which only occurred once in the data that I have, and then 913 years, and it seemed to kind of want to wander to the longer cycles the later in time that we went. So, solar system slowing down. I don't know why that occurs, but that was an interesting. Now, I wasn't expecting that kind of distinct thing. And for anybody that studies beats, you might often find different beats and wonder is that a real cycle or not. Well, what this says is that it may be that they're just different conjunctions that happen at different points in time, but they're all part of the same process. So what I did then was I took, said, well, let's just treat it not as a beat, but as a cosine. And so I created one cycle of a cosine. It was an 883-year long period. So that's this first one right here. And then I took an 854-year cosine and tacked it on the end of that, and so forth and so on, and stacked these all together. And then I found that if I shifted it to the right 100 years, so you can see this is not quite a line there, it's off by 100 years. And then I plotted that just to reconstruction by alley on here. Amazing things jump out. The timing of these points seem pretty good, but what's interesting is they don't happen everywhere. In fact, some places you get double the frequency or half the period where we have a peak here, and then we got some little interesting peaky thing going on here, or here halfway between them, or over here halfway between them. But what caught my eye on this one was that we have our Dark Ages cold period, and then we have 4 cycles of approximately 890 years, and we are 4.7 Ka cold event. So this is the 8.2, this is the 4.7. We go 1, 2, 3, 4 cycles, and here we have the Dark Ages cold period, and then one more cycle gets us into Little Ice Age territory. So that's interesting, and it suggests, of course, that there isn't just a big 890-year sine wave in there, but there's really complicated beat patterns going on within the solar system. Here. I mentioned that we had a peak at the Grand Jovian alignment. There it is, minus 3321. And I didn't push the data this way. This is something I actually discovered later when I was just looking at the numbers. That I know that number. So that's kind of interesting. All right, let's talk about rapid warming and cooling events, and we're almost done here, Tom. So I showed you at the beginning that we had this Younger Dryas, and a 35-60 year shift caused this sudden warming event to kind of line up with that 8.2 Ka event. And I showed you that if we did a 46-27 year shift, the onset of the Younger Dryas seemed to line up with the 8.2 Ka event. And then we had this Lake E5 data where we had this 1850-year periodicity that appeared to bookend the Balling-Allarod interstadial. I don't know how you say that, BA interstadial. It seemed to bookend that, and you can see it up here as well on those lines. Okay, so we've got that bit of information. Then lastly, we have a Grand Jovian alignment. If we keep going back 1306 minus 3321, keep going back a few more cycles, there's a Grand Jovian alignment at 12,506 BC, which seems to line up with the start of the BA interstadial. So I took that as my reference line. Going back to what I said is, well, these seem to be kind of phase reference points. So let's treat this as a timing or a phase reference point. And I came over 1850 years and I drew a line. And then I went from that line over 46-27 years and I drew another line. And from this line, I came back 35-60 years and drew another line. And then I created a 178-year offset, which produced a 178-year offset here as well. Or you can say I came back 46-27 to that line. And then finally, this point here is the very first 883-year cycle that we saw in the 890-year cycle data. And then on top of that, I plotted all 3 of the Martin et al. Reconstructions, name, just 2, and in-grip. And that's a remarkable result. A lot of coincidences in there. I don't have a physical model for it. I don't even have a good reason to explain why I would go 46-27 years from this line as opposed to this line. So there's a lot of question marks. But this is just way too many coincidences, and it's a very interesting result. But it's certainly suggestive that maybe the sun is responsible for these rapid warming and cooling events, which do take a lot of energy. If you're going to heat the Earth up and melt a lot of ice in that short period of time, it's going to take a lot of energy from somewhere. Okay, so let's tie all this together now with harmonic relationships. So I mentioned that we had this 178-year harmonic relationship that we saw in Scafetta's data. Here we're going to be looking at subharmonics, meaning longer in frequency. So if we start with our average Jose cycle, the fifth subharmonic is 890. And then we get a couple more. The eighth subharmonic is 1424, which is near or bond frequency. The 13th is 2314, which might be a nominal Bray-Hallstatt frequency. The 15th harmonic is 26.7, and we saw that in the correlation data. The 20th harmonic is 3560, which is 4 times the fifth harmonic of 890. I showed you a sine wave modulating the Uranus-Neptune conjunctions, and that was a 4271. So here we see that here. And then, of course, we got our 4627. And then in the correlation data, there was hints of 2 others, and there's more behind this than what I'm talking about here. But I think these 2 cycles may be important. They're basically 4627 plus or minus 178. And if we divide this by 2, we get a 2225-year cycle, which is in the Bray-Hallstatt range. And if we divide this by 2, we get a 2400-year cycle, which again is in the Bray-Hallstatt range. So I think there's a possibility that Bray-Hallstatt is actually shifting between 2200 and 2400, which is why I called that the nominal Bray-Hallstatt. Now, if we take the 4627 down here and double it to 9254, I did that so I can get to 1851. And we take the second harmonic is 4627, the fifth harmonic is 1851. The sixth harmonic is, again, something that's possibly near Bray-Hallstatt. And then the 10th harmonic is 925.4, shown here is 925. And then these are the possible things that we saw with harmonics of 7120, 3560, so forth and so on, including 890 fits in there. Okay, so we're kind of at the end here. Let me just summarize things. So climate patterns largely repeat after 3560 and 7120 years, in spite of all those confounding factors we talked about, the quality of the reconstructions, how well does the ice core actually, how stable is the ice core? There's all kinds of things that could go wrong. And of course, the state of the planet is not likely to be identical. In fact, I didn't mention it, but the 3560-year shift on that Greenland data was also accompanied by a -1 degree C shift because the Earth is cooling slightly, or at least Greenland is cooling slightly. We also saw with caveats, solar activity in terms of TSI and sunspot number also exhibited some correlations after a 3560 and 7120-year shift. I don't know how to explain this without the clockwork precision of the orbital periodicities, but I'm open to any suggestions on that. And I've shown you how I got to the 3560-year period, the harmonic relationships with all of the various things we just talked about. And what I didn't talk about, Tom, was that Earth's orbit also affects climate, obviously. Milankovitch cycles, if nothing else. But Earth is not its own thing. It's part of the same club. So Earth is part of the same resonant system that all the other planets are. So Earth is going to exhibit some of the same periodicities in its orbit that we saw elsewhere. So there's going to be some confusion factor about, well, is it coming from the sun or is this caused by Earth's orbit? Maybe length of day is being modulated. There could be all kinds of confounding factors there as well. So I'm not going to talk about that, but I just want to acknowledge that's also a possibility. So that's kind of it, Tom. Any more questions or comments on this?
See, are there any other implications of this work that you did not mention yet in this slideshow?
Well, let's see. I mentioned this will help us kind of figure out what our core data is and how well it works. Nobody's had the ability to kind of compare their data to anything else other than their own interpretation of it. One thing I think is that it's easy to interpret. You know, one of the things that really gripe me about people that have been pushing the CO2 stuff is they create propaganda that's not even mathematically correct based on their own theories in terms of they show a curve of CO2 trending up and to the right, and they show temperature trending up to the right. But you can't establish anything with two trending curves. But here we can show things going up and down and up and down. And I've shown this stuff to a number of people that don't have a background in any of this, and they say, "Yeah, well, it's about right." You know, I don't know. I don't know how to say anything else about that. We do have some interesting impacts in terms of possibly biasing future reconstructions, and that's maybe a point worth making. That this discovery was done without the knowledge of a 35-60-year reconstruction. So there's nobody looking at their data when they're trying to build one of these temperature reconstructions, say, is it A or is it B? And they'll make that decision without this knowledge. Going forward, we can't necessarily make that same claim. So if somebody buys into this 35-60, they may start tweaking their data in that direction. I hope this creates some interest in astrophysics and astronomy research, if nothing else. The signs that the sun are doing it, maybe, and the idea that maybe it's internal oscillations that are causing all of this. I hope some young researcher will take this on. I'm not sure the old guys will. They're kind of set in their ways, but maybe some young researcher that doesn't have a reputation to ruin might be interested in that. So anyway, a few things in there.
Okay, and then I just wanted to mention that you are active on X at rcutler34, right? I have that up in the show description. And then you publish this as a paper. I put a link to that also in the show description.
Okay. Oh, and that reminds me, it's not quite as visible. I'm not sure why. It's easy when I'm logged into ResearchGate to see it, but there's also a link, and you can find that on my X account, or I can send it to you, to a simple Python program. And so you can reproduce this yourself very, very simply. The Python program does all the work for you. It goes out and downloads the data sets and cleans them and plots data with 7120 and 35-60-year shifts. So if anybody wants to go do it for themselves. And one of the reasons, let me see if I can just pull this up a little bit. Are you seeing that, Tom?
Yes. Yep. Looks good.
So one of the reasons for doing that is you might want to go in and do like what I can do here and say, well, let's make sure I got something here. What's going on right here? You know, so we can go zoom in and see, for example, how fast these transitions are. So these things are, you know, that's only from here to there is 80 years at this scale. Actually, no, not 80 years. I'm sorry. These are 10-year intervals. So we can see these rapid changes that happened before. So we're less inclined to think of that as being noise, for example. So if you download that program, you can do this kind of thing where you can kind of go zoom in and if you don't like my number 35-60, you can change that. I'm not sure if I mentioned it, but that 35-60 year in all of the analysis I've done, I never once tried to optimize that based on temperature data and reconstructions. I just found that number and plotted it. And so this was never tweaked to fit the data. Okay.
And then I do see if we go to your paper, there is an email address listed for you so people can contact you there, hopefully.
Yeah, absolutely. So.
Okay. What are you working on next after this?
Oh, well, as I said, kind of at the beginning, I was working on kind of publishing this big, long paper that had all of the stuff I'd found so far. And this discovery allowed me to say, wait a minute, I don't have to include all this complicated stuff about orbits and Jovian planets and all that. All I have to do is say climate repeats and then give a hint in the direction of some of the stuff I've been showing here. So what I want to do next is kind of reformat what I had without this stuff in it, and explain to people why that 99-year moving average works. I'm tempted to actually call it the God filter. There were several times when I was working on that I thought maybe I should start going to church again, because the things that it's doing is absolutely amazing. and not at all obvious from a simple rectangular filter. But it tells us a lot about what's going on in the solar system. So hopefully over the next few months, I'll get some of that out and make that public. I've been kind of keeping that close to my vest because it was my little personal Rosetta Stone to the solar system.
Do you think that these cycles might have something to do with geologic activity on Earth? Do you think that in terms of pulling on the crust and changing volcanic activity, anything like that?
You know, I see people go down that path. I haven't done any research in that area. You know, it seems possible if this is driven a lot by gravitational waves, you know, we're only starting to be able to detect those in the last few decades. It's possible, but that isn't an area I've researched at all.
Okay. Any other points you want to make before we go ahead and finish up?
No, I just want to thank you for the opportunity to do this. It's really hard to get any visibility when you're not well published and you're not academic and that sort of thing. So I appreciate the opportunity to kind of expose this to people, and we'll see whether it gets picked up by mainstream. It's actually doing quite well on ResearchGate in terms of they give you a score in there. I didn't know this, but they give you a score. And this paper, it's only been up for a few weeks. I think last I looked, it was like scored higher in terms of interest than 97% of the papers published in this year. And somewhere around 60% of all the papers on ResearchGate. So I found that interesting. So hopefully there's some interest. And one of the reasons for publishing it there is I wanted people to have a DOI number to be able to reference in their own work. So.
Excellent. Okay. And like I said, people can go ahead and find the link to that in the show description. I will let you go, but thanks a lot for the work you're doing. Hope to have you on again.
Thanks for all you're doing, Tom. It's been great. Thank you.